Hello everyone, hope y'all are doing well. In today's video, we will be talking about a data structure called the zipper. Now, what is a zipper? A zipper is a data structure that can be applied to many abstract data types, such as a list or a tree. Now, a zipper is used in many functional programming paradigms because of immutability. Now, what is immutability? What immutability means is that when we want to update something, we have to create a new object. We can't just mutate something in place. So for instance, if I want to access something like list index 3, I would have to use some sort of pointer to this list to access this item, right? Usually in a language like C++, you would have something like a pointer, right? So we have a pointer, and then this gets us to the third element. But what if you're in a functional programming paradigm and you can't have a pointer and free access for mutation? Well, every time you want to update something, you would have to do this, right? You would have to go to like list at index 3, and let's say you want to change this to a 5, and then you want to do something else like list index 5 equals 8, right? You would have to first traverse 3 indices in order to get to list index 3, and then you'd have to start from the back again and traverse 5 times to get to index 5, right? And this is a lot of wasted calculation because all of this right here you don't want to do. Now, let me propose a problem. So if we were to use this functional paradigm and we wanted to do something like text editing, how would we accomplish this? In text editing, you have essentially a list of characters, right? You have a list of characters here, and then you have something like hello, right? And this is a indexed list, and we want to perform mutations on this list. In order to do that, we would need to index into these different places. But what if we have a cursor, right? What if we have a cursor here? If we have a cursor here, that means that in order to update elements, we would have to move this cursor back left and right. And usually you would do that with things like the arrow keys in Vim, right? If we use the arrow keys and move the cursor, every time we want to update something, we would have to recalculate the index in a linked list, right? Because again, in a functional language, you don't have things like mutable data, which means that you can't easily go from list index 3 to list index 2. This is just a very difficult calculation to do, right? Because you'd have to first go to 3, and then you would have to go back to the root or to the head and then go 2 steps, right? So what is a zipper? A zipper allows us to easily traverse an ordered data structure, right? So let's say we have a list. We have a linked list because linked lists are usually represented as linked lists in functional languages, like Haskell, for instance. So we have a linked list. We have a linked list like this, right? We have a linked list called hello. I'm waiting for this to update. There we go. So if we have a linked list called hello, and we want to traverse this in a text editing sort of manner, then how would we accomplish this? Well, what if instead of having just one list, we had two, right? So if you sort of imagine a zipper, right? A zipper, you have sort of like the little zipper thingies, right? And you have the actual zipper part. If I can kind of draw this, right? You have the actual zipper, and then it keeps on going forward. So this is the sort of like the little thing you actually zip with, and then on either side of it, there's those little teeth that mesh together. Let's name these different sections, right? We'll call this the left side, and we'll call this the right side. And then this is our current value right here. We can even simplify this further by saying that everything, including the value, is the right side. Right. So we have these left elements and the right elements. Now imagine if you were standing at the value here. Imagine if you were standing here at the value. This is you, right? if you sort of look up and look down, or I guess maybe it might be easier still to go left and right, right? If you look right here to your left and to your right, what do you see? Right? You essentially see a stack of items. Think of this as a stack that goes up, and then think of this as a stack that goes up the other way, right? And these are two stacks that help you easily see what's immediately to the left and immediately to the left and to the right of you. Okay, and then what what do I see here? Well, I see a stack, and a stack is a form of a linked list, right? A stack is very easily representable with a linked list. And a stack, you can access this top element at O of one time, and then you can also insert and pop elements in O of one time. So now imagine this. Instead of having a single linked list, we have essentially a stack, right? We have a left and we have a right. Let me actually clear this real quick. We have a left and we have a right. So initially, we're gonna have our zipper looking like this, right? This is our zipper, right? And then there's nothing over here to the left. Now, what can we do here? Let's say we want to move our cursor to the right, right? Well, what we can do here is we can pop off two elements from the right one and then put them into left, right? So it'll look something like this. Let me change the size up, right? This is what our zipper will look like. You can see we essentially popped the H out, inserted it into this stack, and we popped the E out and inserted it here. And then we're left with a right of LLO and a left of E and H. Now let's say we just went 2 right, and we want to go 1 to the left again. That's an L right there. We want to go 1 to the left again. Now in an ordinary linked list, what you would have to do is you would have to essentially recalculate that one jump, right? Well, what we can do with a zipper is we can say, I just want to pop this element back here, right? Which is very simple. We put the E back, and then we pop it from this stack up here. So as you can see, we have achieved O of 1 jumps using a zipper because we just have 2 stacks. And that is all a zipper is. In order to achieve, again, immutability, we are going to do this, right? We are going to maintain 2 stacks, and then it's going to go left, it's going to go right, and then we can pop from these stacks in order to achieve O of 1 time for lookups immediately to the left and to the right. Now, let's actually do a little bit of coding here and see how this is implemented. All right, so if I go back to my editor here, all right, I'm in this zipper directory. Let me zoom in a little bit. All right, I like to make some Clang formats. If you would like to follow along, you can put these formatting styles on, and then I'm also going to make a makefile. In this makefile, I just have some templates right here, right? We're going to compile with everything under source in C++20, and we are going to exec using the main command, right? Sweet, okay. First off, let's make our list class, right? Because in a functional language, again, we have these sort of immutable lists, right? And we're going to take a quick tangent here. I'll leave a bit of, I'll leave a chapter in the description below where we can jump forward to, but we're going to talk about functional lists right now as a sort of reminder on how those things work. Right? So for a functional list, again, it's a linked list, right? We have a linked list here. For a functional linked list, we can also represent this as using a list constructor. What does that mean? Well, a nil is going to mean an empty element. And then a constructor will take it will take some list, right, and some value, and it will return a list, right? So what do I mean by this? We can represent this hello linked list using a list of constructors. So we'll make a constructor using h, and then we will append to it, or we will put h at the front of another list that is a constructor of e, and then we will append to this a constructor of L, constructor of L, and then we'll keep on going until the end we'll have a nil and a bunch of closing parentheses, right? So this is going to be our list, and maybe it'll be easier if I write this using numbers, right? So if we have, let me actually write my data in a different color here. Let's see, it's a nice color here. So we'll have our data as 1, 2, 3, 4. This is our list that we want to represent, right? We have 1, 2, 3, 4. Then what we're going to do is we're going to say constructor of like 1, right? And then we'll go here, constructor 2, if this is sort of making sense, right? And then we'll go constructor 3, constructor 4, and a nil. 1, 2, 3, 4. So this is our linked list, right? This is going to be our linked list that represents this up here. And you'll sort of see what we can do is if we want to add a new element, we literally just take our constructor, right? We just take our constructor and we say we construct with x and our list. This is how we append an element to the list or push it to the front of the list. And then, well, I guess this is prepending. Sorry, this is list prepending. We're going to prepend x to this list. It's going to be at the head of the list. And if we want to delete something, then we can just remove one of these constructors, right? All right, sweet. So now that we've gotten that out of the way, let's go back here and let's start coding our linked list. As always, we have a pragma once. Maybe if I include the once here, and then let's include IOStream. Sorry, let me turn off this. Right, let's include IOStream and let's include memory. Sweet. We're going to define our list terminator, which is going to be nil, and then that's just going to be a null pointer. We should, as mathematicians, we should always define our terms, right? So we'll go template, type name t, right? And then let's make a struct for our list. We're going to make a const t head, and this is going to be essentially the head of the list. And we're going to have a const standard shared pointer const list t tail, right? Now, what this is we're going to have a pointer to the tail of the list, and we're going to have the head, right? So you can sort of think of a list as a node, but in the field of functional programming, this is how we're going to represent a linked list. I'm going to be typing this a lot, so I like to extract this into a define macro so that we don't have to type the shared pointer every single time. So let's define a list pointer that takes some type, and then we're going to do this, and we're just going to say list pointer type, right, just to clean up our code a little bit. So we'll make a constructor for a list that takes a t head and a list pointer for t. That's going to be our tail. And then we're going to say head is going to be our head. And our tail is going to be our tail. Sweet. Now that we have this, let's take a look down here. We're going to make our constructor, right? And we're going to have two different templates for this, or two different like function overloads, right? We're going to have a constructor for when we have a t and a standard null pointer, because typecasting with pointers is a little bit confusing in C++. and we're going to return an std make shared const list t. So we're going to make a list pointer, right? And we're going to allocate memory for this list, right? And then we're going to put the head, and then we're going to put the nil, which is nil is going to be the termination for the list, right? Now, let's come down here, and let's go constructor. But this time, what if we have a list, right? What if we actually have a list as our tail and not just a nil terminator? Well, we're going to do the same, and we're just going to say tail, right? This is very, very simple stuff up here. So now we can have a constructor, right? Now, just for convenience, I'm going to come down here, and I'm going to say template type name t, and I'm going to say void print. This is going to be a helper function for a later print function that we're going to say a list pointer reference to x's, and we're going to say if we don't have x's, we're going to use recursion, because immutability, we can't use something like an index or a pointer, right? We're going to use recursion, and we want to print this recursively, right? So we're going to standard cout the current head, and then we're going to say if we don't have another tail, or if we reach the end, right, we're going to return. Otherwise, we're going to cout a comma, and then we're going to print the tail. There we go. So this is just a very generic recursive solution to printing the list, right? We're going to print the head, we're going to print a comma, we're going to print the tail, unless we catch these guards that are going to prevent us from doing so, right? So now let's go right here, right? And we're going to make our actual print function, which is going to take a list pointer t, a reference to x's, and then we're going to standard cout. We're gonna cout a starting bracket. We're gonna print our x's, and then we're gonna say standard cout a closing bracket. All right, that sounds good. Let's come over here and let's make a main file. So up here, we're gonna include our list.hpp, and we're gonna say int main return 0. And let's say we have a list pointer of integers, and our list is going to be, let's just make it 1, 2, 3, 4. Right, there we go. And this is going to be our list, right? It looked exactly like the one we had over here. Oh, sorry. If that was actually still there, right? We're going to have the list right there, and then we're going to have 1, 2, 3, 4, and a list terminator. So it's going to be a linked list of 1, 2, 3, 4, and we can verify that by printing our list. Interesting. I need to reload my Vim. Make build is out of date. Let's delete build. Let's go here. Let's go here. There we go. So as you can see, we have 1, 2, 3, 4 here, as we expect. And if I just to explain again, we're constructing a list with 1 as the head and a list as the tail, where 2 is the head and a list as a tail, where 3 is the head, the list is the tail, where 4 is the head, and we have a nil terminator at the end of the list. As you can see over here, I kept my promise, right? I kept my promise. We have constants everywhere. There is no mutation going on aside from the stuff that C does, but we can just call that part of the IO monad, right? We have all of this. We have everything is a constant. We're not making any mutations, but we just made a linked list. How great is that? So now let's actually start working on our zipper, now that we've had our zipper, our list class finished. The zipper class is going to be a bit more complicated, but it'll be good. Pragma once again, as we will use, and then we have to include our list HTTP, and we also have to include our memory. This is just going to help us with all the standard shared pointers and stuff. Actually, you know what? We might not even need memory because we already have our list pointer up here. And I think that's all. That's going to be all the memory we need. So if you go template type name t, right? Let's make a struct list zipper. I'm calling it a list zipper because a zipper, again, can be applied to many abstract data types. We're going to make a list pointer t. Let me get a drink real quick. I'm going to make a list pointer t called left, if I can type that correctly. I'm going to make a list pointer t called our right. Again, this is the two ways that you're looking, right? You're either looking to the left or to the right, and you see either one. Now, just to clarify, the head of the right list is going to be our current value. So let's make two, actually, let's just make one constructor here. Let's make a constructor. No, we need two constructors. And I'll explain why in a little bit. Let's make a list zipper that takes a left and a list pointer with right. And then we're going to say left is left, and we're going to say right is right. Right. So we have our left list and we have our right list. Now what I'm also going to do, just for convenience, is I'm going to make another constructor that just takes a some list of x's, and this is going to allow us to pull a list zipper out of a list, right? And what this is going to be is we literally just say left is nil and right is right. Now, why do this? Well, because the head of right is going to have a value. So if you think about it, if we have a list of x's and we want to pull a list zipper out of it, if we initialize it to be the right list, then it'll look identical to a list, right? If we put it in the left one, it'll be the reverse because they're stacks, not queues. All right. So let's make a quick function here called t_extract, and this is going to extract the value out of this list zipper. And I call it extract because list zipper is based on a comonad. And in a comonad, instead of a return as you would have in a monad, you would have an extract that takes the value out instead of like wrapping it in a monad burrito. So we have our extract that will return the value, right? And we'll also have we'll have a left, right? Let's make a left function. Let's make a left called const list zipper t, and then we'll say we have our zipper here, and then we're going to return a list zipper of template t with a constructor of z.right head, z.left, and then z.right tail. Oh yeah, my microphone kind of died there, but we're gonna keep going. We're gonna keep going forward. So as I was saying earlier, right? We have this list zipper, and we're gonna try to move it to the left. So to move it to the left, we can sort of imagine our list here. Let's imagine our list here, right? And then we're going to have our zipper, right? We're going to have our zipper. So we have our zipper like this. Let's imagine we're currently at element 3. Right, that's the big part of the zipper. Yeah, we'll just call it that. Right, we have the zipper here, and then if we sort of imagine this, right, everything over here is the right, and everything over here is the left. If we have this, then we can say that the left is going to be a reverse stack, right? Because the stack goes here, the stack goes upwards. Sorry, the stack. Yes. The stack goes upwards. We're going to say our left is going to be 2 and then 1, and then our right is going to be 3, 4, 5, right? So now let's say we call the function. Left on our list, right? What this means is in order to move left, we're going to have to take this and move it 1 to here. Now, if we redraw this line, look what happens. Our 2 moves from the left into the right, right? It moves from the left into the right. So if we come down here, and we want to move it to that side, if you want to move the zipper to the left, then we're going to have to first off remove the 2 from here, and then we're going to prepend it. We're going to prepend it to right, right? So now our left is going to be just 1, and then our right is going to be 2, 3, 4, 5. Right, so we moved left on our list, and then we should be left with this. Now let's actually take a look at our implementation, right? We have a constructor on right head. And again, I made the promise that we were not going to be doing any mutation in this video. So if we take a look at this, right, we have a list zipper with z right head. Z right head, it's going to be over here, right? Right, and then we're going to construct it with the left. Oh, sorry, I'm looking at this and I completely messed it up. This is actually our move right function, and then this is going to be our move left function. Technical difficulties. There we go. So what we're going to do is, if we want to move to the left, right, we're going to take the tail of left. And again, the tail in a functional, in this sort of functional linked list, it's not just the last element. The tail is not the last element. The tail is everything except for the head. So in this case, 2 would be the head, and 3, 4, 5 would be the tail, right? So again, no mutations. I made the promise of immutability, and then in this case, we're not making any mutations because we're just passing along the value of the tail. Over here, we can see we're essentially prepending the head of left to the right. We're constructing a list from the head of left and the right, right? That's going to be our left. And then right is, as you expect, the complete opposite of left. Quick water pause. Right is the complete opposite of left, where instead of taking the tail of left, we take the tail of right, and then we're saying we're going to construct a list with z dot right head and then with z dot left, right? So that would be the inverse if we instead took the 3 and popped it up here. Pretty simple. Now let's make some functions that'll quote mutate our list, but without doing any mutation. All right. Let me take this. I'm going to copy this real quick. We're going to make an insert function, which is going to insert something. If you sort of imagine in Vim, if you type I, right, it'll insert in front, right? This is essentially what we're going to be doing. Insert function that will take some zipper t, some zipper z, and a type of x, right? So what we're going to do is we're going to say we're going to insert this into the right side. We're going to insert this into the right side. So if we want to do that, we don't want to change the left side, but instead we want to construct something starting with x and ending with the right list, right? This is going to be a zipper that inserts something that like right in front of where our cursor is, if you sort of think of the cursor analogy, right? Well, let's make a drop function. This won't require a second argument. And then if we want to drop something where our cursor is, we're going to just take everything except for the head, right? We're going to take everything except for the head on the right side. So that's going to be our drop function. So again, insert is where we prepend an x to the right side, and then drop is where we just remove the head of the right side by only taking the tail elements. Let's make a final one called modify, and this is just going to allow us to change the current thing, where we're currently at. Let's do this, and then we're going to say constructor using x and then z dot right tail. right? So this is going to just replace the current element with a new one. Now let's make a quick helper function to helper function to convert a zipper into a list so that we can actually play around with it a bit more. Let's make a list pointer. This is going to convert a zipper to a list, and we're going to start with the helper function, right? We're going to take the left side. Let's call it left, actually. We're going to take the left side, and we're going to take the right side. And then here's what we're going to do. Essentially, what we want to do is, because the left stack is reversed, right? Because it's sort of going the other way. We don't want the left stack, right? We want the reverse of the left side. So this toList is essentially just going to pop elements out of left and keep on prepending them into right. So we're going to first do a quick check here. If we don't have a left side, this is our base case, we can just return our right side. And then otherwise, we're going to return toList on, what is this? Let's take the left tail, so everything except for the left head, and then we're going to construct a new list using the head. I keep typing X's for some reason. The head of left and right. So again, this is sort of just popping elements one at a time out of left and prepending them into right. Now let's make an actual function that we're going to call list pointer t to list. And then we're going to take a zipper, right? We're going to take a zipper, and then we're going to say toList using x's dot left, x's dot right. I'm used to Haskell's x's. All right, sweet. So let's take a look at what we've made so far. We have an extract function that does, as you expect, is take the head of right for the value. We have a move left, we have a move right, as I explained in the diagram earlier. We have an insert, drop, and modify that essentially just make copies of the list, right? The insert will insert insert x in front of the right stack. The drop will just remove the head of the right stack, and the modify will replace. So sweet. Now we have a zipper. Now let's go back to our text editing, right? The text input as I was discussing previously. Let's make a text editing program, a simple text editing program. And I promised immutability, so let's make this immutable as well, aside from IO, because IO is, we won't get into that. Let's start with some text, right? We're going to make a list of cars, which is essentially a string, right? And then we're going to, let's start with the text hello. Let's make the text hello. So again, this is our linked list using our list constructors. And if we want to, we can even print this out, right? If we just do a print, L, right? We'll have our string hello. Pretty straightforward. But now, let's say we want to do just a sort of loop, right? So what I'm thinking is we want Q for quitting, right? To be able to quit the program, let's allow the user to print, right? And then let's use like Vim motions, right? So H is going to go to the left, L is going to go to the right, and then I is going to insert, and it'll look something like I like A or something where you want to insert an A, and then let's do X, which is going to drop, and then let's do a R, which is going to be a modify or replace, right? And again, it's going to be like R of A to modify. This will make more sense once you start coding it. So let's make a loop function. Right, let's make a zipper, and then yeah, let's include that. Sweet. So we're gonna start by couting a text input to see what command we want, right? And then this is the one time I break the rule, we're gonna have to use immutability for input because I don't want to write a monad to get the input. Right, so this is going to be our input, and then we're going to say the command equals the first character of the input. Pretty straightforward. So the command is going to be like Q, P, H, L, I, X, R without all the other junk, right? We're going to switch on the command, and we'll just start with the cases, right? You know what? Let's do a Vim macro for this. Let's do a Vim macro for this. First of all, let's clean this up real quick. We're going to go here, QW0, delete, move one to the left, delete again, down, and let's do this 6 times. So now we have each one, and then now let's just turn these all into cases, right? So let's do, I think we can probably just do this with one of these. Actually, yeah, might be easier with a macro. So let's go here, and then let's go 0, case, go here, come down, go down, and then let's do this 6 more times. There we go, we have our cases. So with Q, we're gonna return first. That's just gonna quit our program, right? If we have a P, well, let's print our list. So again, P is going to call our toList function. This is why I wrote the function, right? Because we're able to print a list, and then it'll just be easier to convert it to a list and then print it out. Let's print it out, and then to keep our program running, we're going to loop the spell back onto itself, and we're going to say loop on Z. H, this is going to be our left. We actually want to loop it left, and we also want to return it. And then, yeah, L is going to be the right. L is going to be the right. And then our last couple of ones, insert. Let's insert, and then let's say, yeah, we'll just go straight into the string, right? And we'll say input 2, so this is going to be like A, and then our X is going to be loop of drop, and then our R is going to be modify. And then, yeah, we'll throw a default in here. That'll just crash our program because we're gonna assume that the user knows what they're doing. Sweet. So now we have all of this, and the final thing to do is to start our program. So we're gonna construct a list zipper out of L, and let's run this. Interesting. What am I doing wrong? Warning, list zipper right is initialized with itself. Oh, you know what? Because I decided to do this. This is supposed to be X's. All right. So if we just print it out now, we have our hello, and I want to, how do I make it? Let me think. How should I make this, make a new line? I understand it's because I didn't add a end line here. Right, so if we print it out right now, we have hello, right? This is our starting text. Let's say we want to change that L. I think we should change the second L to a P, right? So we're going to move left 3 times, and our cursor is going to be essentially right here, right? Because we moved left 3 times. Or, sorry, if we moved right 3 times, the Vim motions L, right? And let's replace it with a capital P. Now, if we print it again, you'll see that we're here. But as you notice, all of this is done in over 1 time. We didn't have to go back and go to the nth element. So, case in point, let's go 1 to the left. Let's go one to the left, and then let's replace this with an capital A. If we go here, then we have this one replaced with an A. As you see right here, we're right here. The zipper moved back right here, and then we replaced it with an A, as we see right here. We can do some other stuff too. Let's go left one more time, and let's drop this element. And there is no D command because I called it X. Wonderful. Print. So again, we're gonna move right here. We're gonna replace it with a P. Let's not go right. We're gonna go here. Let's replace it with an A. Right here. All right. So back to here. We're gonna drop with an X this time. If we print it out, you'll see we dropped the element we're currently on. And then let's go. Let's just insert something at the very front, right? So let's go one more time to the left, which should get us right here. And then let's say we want to insert. Let's just insert like a I don't know, Q. Print it out. As you can see, we inserted a Q at the front of this right now. And again, all of this is done with immutability. This is a mutable list that we can traverse in O of 1 time, which is great. And this doesn't mean that we can we can have immediate access into various elements, but as again, I promised that this was an immutable list that we're able to just skip around in. And this has a lot of different uses too, outside of text editing. Text editing is just one that popped into my mind, but one of the tiling window managers I've used previously actually used this, Xmonad. Xmonad used a zipper to manage its windows. If I open a window here, right? If I open a couple of windows here, how is this keeping track of everything, right? You can sort of imagine if we were to make this in a functional language, this would be a zipper, right? It would be a tree. It would be a tree, and then to switch the focus, we would just update the head, right? You can sort of imagine standing here, you have like the right side right here, and you have the left side, right? This is like the zipper head. We have everything to the right here and everything to the left right here. So you can access these in O of 1 time. Now imagine if something like Xmonad didn't have this feature, right? Imagine if Xmonad implemented its windows with a generic linked list. Then it would be incredibly slow to navigate around these windows because you would then have to you would then have to index into these every single time. So just to recap a little bit on what we did today, we made a functional list, which is, you know, not quite an impressive feat. We made a list from scratch, starting with a head and a tail, and we made a constructor function that allows us to build lists, just like this. Next, we made a zipper, where a zipper contains a left stack and a right stack, and it uses sort of this popping to move your focus around in the list. We made a left, a right function, insert, drop, and modify. These are all excellent functions for doing operations on the zipper. You can sort of think like, right, if we had this, right, if we had the tiling window manager, let's say you want to modify one of these windows, right, we can just call modify on the zipper right here, and bam, I'm down here, right? We can switch around these windows really fast. We can drop a window by closing it, right? Drop a window by closing it. We can insert a new window. So now you're sort of thinking about, oh, this is how something like Xmonad would have worked, right? And if you want to take a look at that, I'd recommend Xmonad, right? Xmonad uses a zipper, right? And this is a great article that you can look about how to actually implement something like Xmonad, right? But we have this toList function that converts it back to a list. And then finally, we made an example program of where you would actually use this in the real world, in which case you might use it in a text editing program, for instance, right? So if you sort of imagine you change these standard COUts into actual event listeners for your keyboard, then you could easily make a text program with this. You would have left, right, insert, drop, modify, and to me, this might actually seem a bit more intuitive than maybe intuitive is a strong word, but it's quite easy to see how you would use this for something like quick navigation around in an editor like NeoVim. So that was it. This was my CS final project, and yeah, we talked about zippers today. We talked about lists. We talked about functional programming. It's been a good time. Thank you for watching. And if you have any if you have any questions, please leave them in a comment below. I will take a look, and peace.